This video is going to lead you through where we get the formulas for centripetal acceleration and tangential acceleration using angular polar coordinates. So let's start with looking at uniform circular motion. So this is what we already know. We've already gone through this. And this is what the car looks like when it goes through uniform circular motion. Now this is what the vectors look like as it goes through uniform circular motion. What makes it uniform is that velocity vector. See, when I'm looking at this, the speed doesn't change. In other words, the length of the vector doesn't change. Its direction changes, so that means the velocity changes, but the speed does not change. Let's compare this, or let's look at what we know about this. We know that tangential velocity is equal to omega times r. We know that centripetal acceleration is equal to vt, tangential velocity squared divided by the radius. So I can make a substitution for omega r wherever vt appears, and I get omega r squared divided by r. If I distribute the square to get omega squared r squared divided by r, the r goes out and then the squared goes out, leaving me with omega squared r. So the centripetal acceleration for any circular motion problem in polar coordinates can now be determined as omega squared times r. Alright, so let's group our variables a little bit. Now let's look at non-uniform circular motion, what that looks like. Non-uniform circular motion is one where the tangential speed changes. It increases or decreases. So here's the car going faster and faster and faster as it goes around a circle. So that means my velocity vector in this case is going to change. So when I look at it here, I'm going to look at certain positions of it. So there's a start, 3 seconds, 4 seconds, 5, 6, and you can see what's going on. Okay, it's going faster and faster. That tangential velocity is increasing. So I have a second component of velocity, and that's the tangential acceleration, or second component of acceleration, which is the tangential acceleration. Okay, so here's what we know. I'm going to get rid of this stuff on the side, make a little bit of room. I know the tangential acceleration is a change in velocity over the change in time. Velocity is always final velocity minus initial velocity divided by the change in time. So that's going to be omega r minus omega naught r divided by delta t. So I just made that same substitution. And then I can use the distributive property to pull out the r. And omega naught over t, well, that's just alpha. That's the angular acceleration. So the tangential acceleration, if I regroup my numbers, I can see that it's just r alpha, or r times the angular acceleration. So that's the tangential acceleration. So at this point, in terms of my polar coordinates and my rotational dynamics, or rotational kinematics, I know the tangential velocity, the centripetal acceleration, and the tangential acceleration, all in terms of our polar coordinates. Let's take a look at this car for a second. So I'm going to take one of the cars and I'm going to kind of expand it out, look at the vectors. And with these vectors, I have a tangential acceleration going in the direction of the car, so it's going faster and faster, and I have a centripetal acceleration pointing to the center of the circle. That's still there. Now, as I look at this, I'm going to move my variable over a little bit. So now it looks more like the parts of a triangle, because I have them connected tip to tail. So I'm adding AC and AT, and that gives me the net acceleration. So the net acceleration is the hypotenuse of a triangle, where AC and AT are the two legs of the triangle. So that's great. So when I need to find the net acceleration is just found from Pythagorean's theorem. So A net squared is equal to AC squared plus AT squared. And if I have the A net, of course, that means I can also find the net acceleration of anything going in a circle. Now, it doesn't have to make a complete circle. It can just go in part of a circle, a circular path, circular arc. For example, a pendulum. You could use some of this analysis on a pendulum as well, because it's going on part of a circular path.